Okay, so today we're going to look at 3.5. And as I said before, it's basically doing what we did in section 3.4 again, except now with imaginaries. All right? So, reminder, I've said this a bunch of times, okay, I'm just kind of making it sink in. A number is a 0 if you plug it in for x into a function, and the answer comes out to 0. Okay, that's what it means for a number to be a 0. It also means that your graph has an x-intercept at this coordinate, c, comma, 0. So now, what if you had a graph that doesn't cross the x-axis? What do you think that would mean in terms of real roots? There are none. Right? We looked at one like that in the homework. So, if you have a polynomial that does not cross the x-axis, there are no real roots. Doesn't mean there's no roots, period. Okay? Every problem has roots. It's just, sometimes they're real, sometimes they're imaginary. Let's look at this one. So, let's say I set this equal to 0 and had you solve it. What's going to happen when you try to solve that? It's going to be the square root of a negative, right? So now you take the square root of each side, and that's the answer. It's the positive and negative square root of -1. But if we try to do the square root of -1, so let's just quit, second, square root, -1. It says error, and it doesn't say that it's like a domain error or I did like a divide by 0. It's not like I did something wrong, it's just the calculator says it's not a real answer. Okay? So we got to figure out a way to represent it, because if we take the calculator and press mode and change it to that mode, instead of real, we change it to a plus bi. So basically real, it's like the calculator knows algebra 1. Once you turn it into the a plus bi, now it's like you just taught it algebra 2. So now when you ask it the same question, it doesn't tell you that it's a non-real answer anymore. It tells you what the answer would be if you go outside the real number system. It's I. So we're going to talk a little bit about what I is. So first of all, what's in that red box is a definition. I equals the square root of -1. If you ask me why, I will say because it is. It's like if you ask me why do parallel lines never cross? Because they don't. It's just one of those things in math that it's like what they call a postulate. It's not something you prove. It's something that you start with and you say, okay, we're starting with this. Does everyone agree on it? Okay, we all agree on that. Now we'll use that to figure out other things. Okay, so I equaling the square root of -1 is a definition. You cannot prove it. But as long as we all agree that I equals the square root of -1, we can figure out other things that can be proved. Like this, I squared. So that basically means this. So what would I squared come out to? -1. So sometimes you do some arithmetic with imaginary numbers and you get a real answer. Right? Sometimes you do, sometimes you don't. Depends on the problem. I showed you what I squared is because that is going to come up a lot when we get into foiling. Okay? So any questions on that idea? This definition, and then how I proved I squared was -1. How about I cubed?
-I.
Yeah, if you think of it like this. Think of I cubed as I squared times I to the first. Well, we just did I squared, that was -1. And then think of it like that. I cubed is -I, which we normally write like this. How about I to the fourth?
1.
That's 1. And if you're like, how's that 1? think of it as I squared times I squared. We just said I squared is negative 1. So negative 1 times negative 1 gives you 1. Now, if we keep going, you're going to notice something happen now. I to the 5th. Think of it as, how could you think of that one?
I.
I to the... And what did we just say I to the 4th is?
1.
It's just 1 times I, which is really I. So now we're back at the beginning. I to the 6th is I to the 4th times I squared. I to the 4th is 1, so it's like you don't even have that. So I to the 6th is the same as I squared. I to the 7th is the same as I cubed. I to the 8th, there's a pattern. Okay, it just keeps repeating from here. All right, but the ones that we really need to know are I squared. Okay, that's the one that's most important. So if you ask me what's I to the 300th power, all I have to really do is figure out how many I to the 4ths can I take out of that, and then look at what's left. Okay? And I can figure it out very, very easy. Okay? All right, so now if you take I and you plug it into the equation we have right here, x squared plus 1, we've already kind of figured out what's going to happen. But if you plug in I, it's like almost like we're checking our answer. I squared is negative 1, and negative 1 plus 1? 0. So what I just did is I proved that I is one of the roots of that equation by checking it. Okay? Negative I also is, right? But we'll talk about that later. So a complex number is written that way. It's in the form a plus bi. A is the real part, b is the imaginary part. These are all examples of complex numbers. 3i. What's the real part with 3i?
3. 0.
0. Right? You think of it like this. There is no real part. Same with negative 7i. These first two are what we call pure imaginary numbers, which I think I write that. Okay, so yeah, pure imaginary number. That is still considered a real number, a complex number as well. But we actually just call it a real number because you think of it like this. There is no imaginary part. 4 plus 0i. So this is one that actually has both a real and an imaginary part that are not 0. Real part is 2, imaginary part 3. Okay, that's how you would describe that one. What's the real part here?
2/5.
And the imaginary part?
Negative
1. Yeah. The I is just there to tell you what's in front of it is the imaginary part. Okay, so the next thing, what does it mean for two complex numbers to be equal? Well, if we had two numbers, just like real numbers, and we asked if they were equal, all you have to do is look at one thing and compare it to the other one thing, right? With complex, it's a little bit different. If two complex numbers are equal, you have to look at two things in each number. You have to compare the real part to the real part, and the imaginary part to the imaginary part. So an example of two complex numbers that are equal, 2 plus 3i, and 2 plus 3i. Okay? The real parts match, and the imaginary parts match. Now, if you did something like that, you could say, well, they're partly equal, but that means they're not equal. Right? The real parts do match, but now the imaginary parts don't. Okay? So what I'm saying is both the real and the imaginary parts have to match to say that this complex number is the same as this one. All right. Now we're going to look at a quick review of adding, subtracting, multiplying, and dividing, and then that'll finish the review part. So, we can treat I as a letter when we're combining like terms. And if you're thinking, well, yeah, I is a letter. No, not when we're doing complex arithmetic. If you say I is a letter, then it's like you're saying this is a letter. Not in math. In math, that's not a letter. We don't use that as a variable ever, right? Variables are letters. But you'd never see that as a variable because it stands for 3.14. Right? When you're doing complex arithmetic, you would never see I as a variable because it stands for the square root of -1. I is a number, just like pi is a number. Any question on that? Okay. So I is a number. But if you treat it like a letter, just like you could treat pi like a letter, and if you had 5 pi plus 2 pi, you could say 7 pi, right? It's combining like terms, just like you could do 5x plus 2x and say 7x. Right? So you learn how to combine like terms with letters. It does work the same if you treat pi as a letter. Okay? Same thing here. If you treat I as a letter, the arithmetic will work out. But just always remember, I is really a number. All right. When we multiply complex numbers, foiling comes up a lot. And that means I squared comes up a lot. If you leave a problem with an I squared in it, then it's wrong. Okay, so don't leave I squared in the final answer. Always change that to -1. And then that usually means you can combine it with something else. When we do division, I'm going to show you what's called a conjugate. And let's look at what happens with square roots. So, with square roots, okay, if you have a negative under the square root, what number is really in front of the x?
I.
Nope, not an I.
-1.
-1. You could think of it like that. That's the same thing. And now, when you have a factor like that, you have two numbers multiplied together under a root, you can separate it into two different roots. Okay, just breaking out the -1 under one of them and the x under the other. And now we just defined that. What was the square root of -1? I. So what basically happens when you take a square root of a negative number, the negative comes out in front as an I. And this is the reason why. Now there's two different ways you can write your answer. If your answer has an I in it, I would write it like this. Why would I not do this? Yeah?
So it could be confusing on if the i's in the underneath the square.
Yeah, I can't really tell. Is the I supposed to be under the square root? Is it not under the square root? Put it in front and that eliminates that problem. Now, if you don't have a square root in your answer, we usually do put the I at the end. Okay? We usually don't write I5. We just put the I in front when there's a square root. So, let's try these. How about, Vinny, what's the square root of -4?
2i.
2i, yep. So you have 2i. How about the square root of -7? Yep.
Would it be I square root of 7?
Yep, that's one of the cases where you should put the I in front. How about square root of -9? Yeah.
3i.
3i. And how about the square root of -20? Yeah.
2y times the square root of 5?
Yeah. So if it was the square root of 20, it would just be 2 square root 5. Square root of -20, 2i square root 5. So any question on simplifying square roots? Okay. So let's add these up. So to add, I'm just going to do one of each. One add, one subtract, one multiply, one divide. Just right through. Think of it as combining like terms. If you can do this problem, 7 minus 3x plus 4 plus 5x, it's exactly the same idea. Great. So when you combine your like terms here, Zach, what are you going to get for a real number?
You get 11.
11. And what am I going to get for an imaginary? Yep.
2i.
Yep, 2i. And that's it. So you can combine real numbers with reals and imaginaries with imaginaries. Okay. Any question on that? Let's look at this one. When you subtract, it's the same idea as addition, except this negative applies to both. It's really like a -6 and a -I. You're subtracting the whole thing. Right, so Libby, when I do that, what is going to be the real part?
-2 minus 3i.
Yep, so which part is the real part?
-2.
Yep, so -2. And then she said minus 3i because you have a -2i and you're minusing another I from that. Okay, any questions on that? All right, let's look at multiply. So when you multiply, it's FOIL. Okay, so if I was reviewing this in like an intro to trig kind of class or algebra 2, I would write this all out. When distributing, it's like doing first, outer, inner, last. But I'm not going to write all that out. So let's do it. Skylar, what do you get when you do 2 times 5?
10.
So 10. And Peregrine, 2 times -I?
-2i.
And I'm going to do this at the same time. What's 5 times 3i?
15i.
15i. So I'm going to combine -2i and 15i. You get that. And now 3i times -i. First of all, what's positive times negative?
Negative.
The negative. And now you've got a 3i times an i. That's 3i squared. Now, what did I say earlier about that?
That's -1.
Right. I squared is -1. So it's really 10 plus 13i minus 3 times -1.
So would it just be plus 3?
So really, that's 10 plus 13. -3, or 3 times a -1 is -3, and then you're subtracting -3. That's really plus 3. And now you can combine.
So 13 plus 13.
And just a coincidence they came out to 13 and 13. So that's how you multiply. Any questions on that? Okay. And divide. So in order to divide, you have to use what's called the conjugate. So the conjugate is basically when you just negate or change the sign of the imaginary part. Okay, so we'll just practice finding a few conjugates, and then I'll show you how to use a conjugate to do division, and then we'll finally get to the stuff that's important. I mean, this is important, but this is really review. So the conjugate is when you change the sign of the imaginary part. So if you had a plus bi, the conjugate is a minus bi. So if I had 3 plus 2i, what would be the conjugate of 3 plus 2i?
3 minus 2i.
3 minus 2i. If I had 4 minus 5i, what's the conjugate there?
4 plus 5i.
4 plus 5i. How about 3i? Yep, negative 3i. And 6.
Just 6.
Just 6. And if you're like, well, what? I thought you were supposed to change the sign. Think of it like this. It's 6 plus 0i. There is no imaginary. So the conjugate is 6 minus 0i. Plus 0 minus 0, it still stays as 6. Okay. Questions on finding a conjugate?
So if there's no I part, technically it just stays the same.
Yeah, real numbers are their own conjugate. Yep. So, in order to divide two complex numbers, we really do it like a multiplication problem. We multiply the top and the bottom by the conjugate of what's in the bottom. And the reason we do that, well, you'll see in a second, but you're not allowed to leave an I in the bottom. It's kind of like leaving a square root in the bottom. We don't do that. So, if you multiply top and bottom by the conjugate, something kind of nice will happen. But it's got to be the conjugate of the bottom. So, I usually just start by putting parentheses because we want to remember there's going to be distributive happening. And what am I going to multiply top and bottom by here?
2 plus 3i.
2 plus 3i. So 2 plus 3i. 2 plus 3i. Okay, let's do the top first. So 5 times 2 is going to give me 10. 5 times 3 is 15. And 2 more. So 17i. And then see if we can do it all at once. I times 3i. 3i squared. So that's really minus 3. Okay? Now, watch what happens in the bottom. So when you FOIL it, 2 times 2, 4. 2 times positive 3i, 2 times negative 3i. That cancels. When you multiply conjugates, you never have to worry about the outer and the inner because they're going to cancel. So all you're left with is first and last. So we got the first, negative 3i times positive 3i. Well, negative times positive is a negative. And what's 3i times 3i? So if you need to write it off to the side, that's a 9i squared. That's going to go right there. But what is 9i squared? It's negative 9. So we end up with 7 plus 17i all over 13. Now that's not standard form. Standard form should have a real part and an imaginary part separate. It's very easy to change that to standard form. There's your real part. 7/13. Imaginary part. 17/13. So if they ask for it in standard form, you do have to do that last step. Just separate it into 2. Now, it's kind of a shortcut. If you take 2 and square it, what do you get? And if you take negative 3 and square it, what do you get? If you add those two numbers, it'll always give you what goes in the bottom. So if I wanted to FOIL 4 plus 5i and 4 minus 5i real quick, square the 4, square the 5, just the 5, 25, add 16 and 25, and that's what you're going to get when you FOIL. That's what always happens. So it's just that number squared and that number without the I squared. And if you said, well, should I use the negative 5? It doesn't matter. Square 4, you get 16. Square negative 5, you still get 25. So you just square each number. If that shortcut's confusing, then don't use it. Just FOIL it every time, and you'll get the right answer anyway. Right? Conjugates are quick to FOIL. Non-conjugates are not. You got to do the whole thing. There's no shortcut.
So if you go to the next slide where you're doing the shortcut, wouldn't 25 be, wouldn't it be times negative 1 though? Because It's 5i squared.
It would be a negative 25i squared.
Oh.
Because positive times negative is negative. And then you get the I squared, which basically cancels that negative.
Right. Okay.
So it ends up as a positive 25 and a positive
And that
16.
works when you're doing the conjugate.
Only with conjugates. Yeah. Yeah. Okay, so now let's apply what we just went over to find the zeros of this different equations. So now we're looking for all zeros. Rational, irrational, imaginary, okay, all of them. What's nice about finding the zeros of this one? It's what? It's already a degree 2, which means it's a quadratic. We already have a way to do that without anything fancy. What's the way we can do it? We could try factoring it. I'm not sure that's going to work here. So what else could we do? Just use the quadratic formula. So what's A? 1. B? And C? Wow, there we go. A, B, and C are all 1. So negative B plus or minus, what's B squared? 1. Minus 4 times A times C, all divided by 2. Negative 1 plus or minus, what's 1 minus 4 times 1 times 1?
Negative 3.
So it's negative 3. The only thing we have left to do here is what I just, well, a few slides ago I had you guys simplify square roots. So what is the square root of negative 3? Just I square root of 3. What kind of answers are those? Real or imaginary? They're imaginary. So if you were to graph this, what do you know would not happen?
It wouldn't touch the...
Wouldn't touch what?
The x-axis.
Would not touch the x-axis, ever. So there's still 2 answers. Whatever your highest exponent is, that's how many answers the problem has. In this case, they're imaginary. Okay? And if you wanted to write it in standard form, you technically would write it like this. Negative 1/2 plus or minus root 3 over 2i. That's putting it in a plus bi form. Now, what do you notice about these 2 answers? Negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. Those 2 answers are what? What's the connection to each other?
Both fractions.
They're what? They're conjugates. Okay, they are conjugates. Negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. And every time you solve a problem, imaginary answers always come in pairs. Specifically, conjugates. So if you know that a plus bi is a 0, right? It's a complex number that is a 0 to your equation, then you automatically know a minus bi is a 0 to your equation. So complex answers always come in pairs. And of course, if b equals 0, then that doesn't really apply, because all you have is a real number. Okay? So we're talking about when you actually have a non-real, a non-zero imaginary part. Okay, so all the stuff that we've learned this week, remainder theorem, factor theorem, synthetic division, they all work with complex numbers. Right? So if you want to know if a complex number is a factor, divide by it, and if something is a factor, what do you get for a remainder? 0. That's what the factor theorem said. Right? So we can still use that. Synthetic division is a little more of a pain because of the amount of distributive property you have to do. But we'll try one. Okay, let's try this one. This one's a little bit longer than I'd probably do on a test. I'd probably give you a cubic on a test. It would just reduce the number of distributive properties by one round distributive. But let's try this one. So I'm going to show that 1 minus 2i is a 0.
Is that 17x?
That's 17x squared, yep, plus 14x plus 65. Now, remember what I showed you before. Let's call this C. If you know that C is a 0, what is a factor? X minus C is a factor. That's what I'm really going to show. So what does that mean I'm really showing? I'm going to show that this is a factor. It's really x minus c. If you wanted to distribute it out, it's x minus 1 plus 2i. I'm showing that that is a factor. X minus c. So, put what comes after the minus sign on the outside of your bracket. That's what's after the minus sign. And now fill out all your coefficients. Leave a little more space between the columns because each answer is going to be complex, so you need a little more room. So 4, what would be my next coefficient?
0.
Yep, 0, and then 17, 14, 65. So when I'm done, it'd be great if I get negative 65 right here, and then negative 65 and 65 gives me remainder 0. That's what I'm hoping happens. Okay, this doesn't start off too bad. Bring down the 4, and this distributive property is the easiest one you'll have in the problem. 4 times all of that. 4 times 1? 4. 4 times negative 2i. Now it gets worse. So, add these up. 0, 4 minus 8i, that's still easy. Now it's a distributive property. It's 4 minus 8i times 1 minus 2i. I'm going to do that off to the side so I can kind of keep this clean looking. So we got 1 minus 2i times 4 minus 8i. All right, 1 times 4? 1 times negative 8i? And, yeah, negative 8i, and then another negative 8i. So what's that? Negative 16i. And negative 2i times 8i. That's 16i squared, which is what number? What's 4 minus 16? So negative 12 minus 16i. You're never going to have like terms in these columns to combine for imaginaries. Just reals. So we'll do that right now. Yep.
Yeah, I'm gonna.
Okay, so I just did 17 minus 12. Okay, now let's do it again. What am I going to multiply this time?
5 minus 69 times 1 minus 2i.
Yep. So now FOIL that. 1 times 5, negative 16 minus 10 is how much? Negative 26i. Negative 2i times negative 16i. That's 32i squared, which is negative 32. What's 5 minus 32? Negative 27. Minus 26i. And if this was a test, this would probably be the last step. Okay, but we got one more. What's 14 minus 27?
Negative 13.
Negative 13 minus 26i. Now, I already know what I want to happen. I want to get negative 65 right there. So somehow I'm hoping all my i's just disappear at this step. See what happens. Okay, so we've got 1 minus 2i times negative 13 minus 26i. 1 times negative 13 1 times negative 26i. And negative 13 times negative 2i. Positive 26i. That's good. Negative 2i times negative 26i.
13.
So positive, that's a positive 52i squared, which is what number? And what's a negative 52 and a negative 13? Negative 65. So I have just shown that 1 minus 2i is a root. So on a test, like I said, I would eliminate one of these columns because it starts to get a little time consuming. So it'd be one step shorter.
So that's how you prove it?
That's how you prove it. Yep. Yeah.
Do you have to write the quotient over?
No, the quotient doesn't really make sense here. It's, no. No, I'm going to talk a little about that, but no, you wouldn't have to. Okay, odd degree polynomials will always have at least one real zero. What's another way of saying that? You always have, think about what real zeros mean visually. Yeah?
That means there's at least one x-intercept.
Right, why? Why do odd polynomials have to cross the x-axis once? Yep.
Because they have opposite end behaviors.
And one other thing.
Like they go on forever. Because like if they have opposite, then it has to at one point.
Thinking one word you could say that would, just because a graph goes on forever in opposite directions, doesn't mean that it passes through the x-axis, unless the graph is continuous. So polynomials are continuous. One goes up, one goes down. You're going to have to pass through the x-axis somewhere, at least once. That's the reason why. Great. So find all zeros of x cubed minus 1. What theorem could we use to give us a starting point for finding roots? Yep.
The real or the rational root theorem.
Yep, we're going to do the rational root theorem. If you know how to factor the difference of two cubes, you would already be probably done this problem. But if you don't remember the formula for the difference of two cubes, that's fine. We can figure it out this way. What are your factors of, I guess, both p and q? So when you take all the p's and divide by all the q's, your list of possible rational roots are what? Just 1 and negative 1. Now, at this step, I would normally say graph it and see which one it looks like, but I can just plug those numbers in quicker than graphing it. So which one of those numbers can you plug in? Yeah.
I was just going to say, like, because we already had a problem like this on homework, so we would just factor into, like, x, and then x minus 1 and x plus 1. So, like, we already know that our zeros be 0, 1.
You can't factor an x out of this because this term doesn't have an x. If that term had an x, then absolutely, you could do what we just did on the homework. Yeah. So, does anybody see what number you can plug in for x and it will be a root? Yep. 1. So let's start making a list of roots. 1. And it says find all. All means imaginary, real, all of them. So since 1 is a root, what am I going to do now to turn this cubic into a quadratic?
Synthetic division.
Yep, synthetic division. So we have a root, and we're going to have 1, what are my other coefficients? 0, 0, negative 1. Lots of zeros and ones. It's going to be very, very fast. So 1 times 1 is 1, 1 times 1 is 1, 1 times 1 is 1, remainder 0. Okay, so we know 1 is a root. I'm not interested in the remainder, I'm interested in the quotient. What is the quotient? So now, find the zeros of that factor. But x squared plus x plus 1, we just did that. X squared plus x plus 1. So the two other roots are negative 1/2 plus or minus root 3 over 2i. So -1/2 plus or minus. So you'd have to go through and finish that with quadratic formula. But we've already done it. In example 4. I'll just put that here. I think was it example 4? Did that? I think it was. Any question on that one? Now, I'm not saying this is the fastest way. If you know the formula for the difference of two cubes, that's faster. But this works. All right. So if you go back to example 6, this problem, 0 equals x cubed minus 1. That's what we just solved. Well, that's basically like saying solve this. 1 equals x cubed. If you thought about it that way, how would you undo cubing? Take the cube root. So this is the same problem, right? What we really did in this problem is we found all the numbers that are the cube root of 1. That's what you just found for x. That's the cube root of 1. And those are also the cube roots of 1. Because if you plug them in and cube them, you get 1. And 1 minus 1 is 0. And that's what we just found. We found the zeros. So all of these numbers, if you cube them, you get 1. So if you cube something and get 1, that means that it is the cube root of 1. So we really found all 3 cube roots of 1 in that last problem. Now, the book calls it, I don't usually use this term, but if you see the term unity, that means 1. And when you're solving this equation, x to a power minus 1 equals 0, just like we had right here, x to a power minus 1 and set it equal to 0, you will always get as many answers as the highest exponent, as that exponent right here. Right? So if you made that exponent a 4, which I think is what I'm going to do in the other problem, you're basically solving for 4 numbers that you can raise to the 4th power and get 1. So a couple of those are easy. 1, negative 1. If you raise 1 to the 4th power, you get 1, and 1 minus 1 is 0. So 1 is an answer. Negative 1 to the 4th power is also 1. 1 minus 1 is 0 again. The other 2 answers are imaginary. Right? But there are 4 of them. Okay, actually, let's try that problem. I'm going to pretend that we didn't know 1 and negative 1 were already answers, because you might not guess that. So, to find the nth roots of 1, this is the equation you set out. And we're doing it for 4th roots. So that's the equation that you want to solve. Any questions on that equation? You're looking for numbers you can raise to the 4th power and have them come out, have that come out to 1. That's what you want. And then 1 minus 1 gives you 0. Now, this factors. That's a difference of 2 squares. Anyone tell me how that left-hand side would factor? If you didn't recognize the factoring, this one's a pain. You're going to do the rational root theorem. You'll figure out that 1 is a root, and then you're going to divide through synthetically by it. Now you'll have a cubic. Then you're going to see, oh, negative 1 is also a root. And then you're going to do synthetic division again, and now you're going to have a quadratic. But if you can see how to factor it right away, you can avoid all that synthetic division. If not, then you have to do it. Yep.
So is it just x squared plus 1, x squared minus 1?
Yep. So you automatically got it down to quadratics that don't even have linear terms, so it's very easy to solve. Set each factor equal to 0. Let's start with the one on the right. If you set that equal to 0, What do you get for x? 1 and -1. Which you could have gotten from synthetic division if you didn't know how to factor it. Now, how about this one? Subtract the 1. What do you get here?
I squared root of 1 squared.
So you get I and
-I.
-I. There's your 4 answers. I, -I, 1, -1. And I'm not going to graph those answers, but once we learn how to graph complex numbers, these 4 answers would be the 4 corners of a square if you drew it. If you had 5 answers, they would be the 5 vertices of a pentagon. If you had 3 answers, they'll be the vertices of an equilateral triangle. So there's actually a pattern to these answers. If you know one, you can figure out the other ones kind of geometrically. But we're not going to get into that. Any questions on those answers? Okay. So, I've already kind of pointed this out to you, but the idea is that the total number of zeros that you get is equal to the degree of the polynomial. Okay? And I might just have you write the second thing down rather than what I just covered up. But that's important. The total number of zeros is always equal to the degree of the polynomial. Okay, and I'm just going to have you write this one.
Oh, what was at the top there?
The total number, the fundamental theorem of algebra?
No, yeah, just actually at the top.
Just the top part, yeah. I'm going to have you write the next one because that one is more important. So, keeping that in mind, let's say you had a cubic. How many answers does that have? 3. What would be some scenarios you could have for real and imaginary?
1 real, 2 imaginary.
Yep. You could have it cross the x-axis 1 time and get 2 imaginary.
2 real, 1 imaginary? No.
Imaginaries always come in pairs. So you couldn't have 2 and 1.
3 and 0.
You could have 3 and 0. I'm not saying that these 3 are unique. I'm just saying maybe it's a repeated group. We've seen that kind of thing happen. That still counts as a second answer. It's just it's a repeat. But for a cubic, that's all that could ever happen. Right? And we could look at like a quartic. How many, what are the options here?
2 and 4. 0.
You could get 2 real, 2 imaginary.
2 and 4.
You could have 0 real and 4 imaginary.
4
real, 0 imaginary.
Or 4 and 0. This middle one could look something like this. A W shape that's shifted completely above the x-axis. This bottom one could look just like this, but just move the W shape down. Now they're all real. And 2 could look something like this. It would come down, cross through, and maybe make a W shape like that. So now you only have 2. Yep. Just possible options, right? So kind of keep that in mind, right? You can never have an odd number in the imaginary column, right? So you couldn't have like 3 and 1. No, it doesn't work. All right, so the linear factorization theorem, bless you, basically says that if you have a polynomial and the degree is greater than 0, so linear, quadratic, cubic, or higher. Right? If you've got a polynomial with a degree greater than 0, then it will have as many factors as the highest degree. Well, that's the same as saying it has as many roots as the highest degree. If it's a cubic, you will have 3 answers, and it would factor into 3 things. At this point, you should be able to do that. Not as quick, no, I couldn't even do it that quick. But you would write out all the rational roots and go from there. Okay. If it didn't factor nicely, then you wouldn't be able to do it. Okay, this one factors very, very nicely. In fact, all the roots are rational. -1, -2, +3. Okay, so it's cubed, 3 factors. Here's one that's a 5th degree polynomial. And you might say, well, that doesn't really have 5 distinct factors. You're right, they're not distinct. They don't have to be. You can have repeated roots. Okay. So this is a degree 5. And it does have 5 real answers. There's just some repeats. That's all. Any questions on that? That something will factor into as many sets of parentheses as the highest exponent. Okay. So I've just kind of been saying to you the root is repeated. The actual term, it's called multiplicity of the root. So -1 is a root that's repeated twice, or you say multiplicity 2. 2 is a root that's repeated 3 times, so you say it has multiplicity 3. Okay, so any questions on that? All right, so really quick review of complex numbers. I know that was pretty fast, but what I really want you to be able to do is something like that. Now, in the homework, and definitely on the test, you're going to see a problem where I say something like, find a polynomial with given roots. I'm going to write down one like we did 2 days ago, and then I'm going to do one kind of incorporating today's stuff. So if I said to you 2 and 3 were roots, what would that mean are the factors? Yeah, so you FOIL that out and you're done. Now, what if I said to you 2 plus I is a root? What else do you automatically know? There's something else you know I haven't written.
2 minus I is a root.
2 minus I has to be a root. Because remember, roots always come in pairs, conjugate pairs. So if I tell you 2 plus I is a root, you have to know that this is also a root. That's the first part. Now the second part. If 2 plus I is a root, what is a factor?
X minus 2 plus I.
X minus 2 plus I, and 2 minus I. Now, that looks like it's a mess, right? It looks like there's all kinds of a mess going on there. Not really if you FOIL it out. It's X minus 2 minus I, and X minus 2 plus I. They're not like conjugates exactly, but you do get some stuff that will cancel out. Let's FOIL it and watch what happens. Okay, so we're finding a polynomial that has these 2 numbers as roots. First of all, when I FOIL it, what's going to be the degree? 2. 2 roots, degree 2. 2 factors, degree 2. It all goes together. Okay. So x times x gives me what? And then x times -2. And x times I is just x times I. Now that's weird, right? X times I, that's kind of a weird looking thing. We're going to hope that that just disappears and we get a -I times x somewhere later on. Okay? But you shouldn't have any x's with i's next to them when you're done. All right, what's -2 times x? -2 times -2? And -2 times I. -2i. Also, what should end up happening is there shouldn't be any i's left. Not only i's with x's, but i's with numbers. Because if I'm asking you to find a polynomial, you're not allowed to have i's in the answer. So these i's better all start going away pretty soon. Negative I times x. Negative ix or xi. What's negative I times negative 2? There's a plus 2i. And negative I times positive I. So negative I squared. Now, look what happens. Plus 2i, minus 2i. Minus xi, plus xi. All the i's disappear. So when you're finding a polynomial with imaginary roots, when you do this, all your i's should just go away. So x squared minus 4x plus 4 plus 1. That's the answer. X squared. So x squared minus 4x plus 5. That's a polynomial that has these as its roots. A little more work to FOIL, but really a lot of it just cancels out. That is definitely on the test on Friday. Okay, so homework. Tonight it's on 193. And it's 1 through 3, 8, 9 through 13, 15, 19 to 22, 25 to 27, and then it just jumps around to some singles. 32, 36, 39, 40, 47. I think half of that is basic arithmetic review, and then the other part is what we did in the second half.
Is